You have two more problems in your guided notes to just practice the central limit theorem and sampling distributions a little bit more. So the first one is the length of a hospital stay. It says the average length of a hospital stay in the US is mu equals 9 days with a standard deviation of sigma equals 3 days. And then you have one on ACT scores as well. So I would love for you to pause the video and give both of those a try. Okay, so this hospital stay one, it says the average length of a hospital stay in the US is mu equals 9 days with a standard deviation of sigma equals 3. If a single patient is selected at random, what do we need to know or what do we need to assume to proceed? So what we would need to assume here is that those lengths of stays in the hospital are normally distributed. Okay, so if we don't know that, then we're going to not be able to use these techniques that we've learned in this class in chapter 3 and 15. But let's go ahead and assume that it is normally distributed, and then we'll answer these questions. So for a single patient, one person selected at random, that population distribution, if we assume the normal, is going to be normal with a mean of 9 and a standard deviation of 3. So go ahead and put those in and scale to fit. And then we're interested in the probability that they stay less than 9.6 days. So I do have the less than side shaded here. So that probability is almost 58%, 0.5793. And then it says, assume a simple random sample of 100 patients is selected. Our sampling distribution here, so we're over that size of 30. So we definitely have normal no matter what. And then we still have the same mean of 9, but I need to take that standard deviation of 3 and divide it by the square root of 100, the sample size. So that gives me 0.3, and then I'll rescale this. And so now the probability that 100 patients, their average stay is 9.6 days or less, is almost 98%, 0.9772. And then ACT scores, it says the scores of students on the ACT college entrance exam in a recent year had a normal distribution with mean mu equals 18.6 and a standard deviation of sigma equals 5.9. So do we need to use the central limit theorem here? And the answer here is no. If the original population is normal, it doesn't matter the sample size, and we can just proceed on to that sampling distribution. So because it's originally normal, we don't need the central limit theorem here. We need that central limit theorem when we're looking at samples that aren't normal or original populations that aren't normal. All right, find the probability that a single student randomly chosen scores 21 or higher on the ACT. So I do have a mean of 18.6. and a standard deviation here of 5.9. We'll scale to fit. And then we're looking for the possibility that they score 21 or higher. So I'm going to flip that inequality so I get that right side highlighted. So the probability that one randomly selected student scores a 21 or better is about 34%, 0.3421. And then what is the probability that the mean score of 50 randomly chosen students is 21 or higher? So we already have normal from the original population. We keep the same mean of 18.6, and we'll change that standard deviation to be 5.9 divided by the square root of 50. That's going to give us about 0.834. And if I scale to fit, now the probability that 50 students as a group average a score 21 or higher is 0.2%, so 0.002. So pretty minuscule there.